Okay, in this video, let's talk about section 13.3. Geometric sequence. And geometric series. Okay, so first, what is a arithmetic sequence? Remember that arithmetic sequence the recursive formula has an important part that an minus 1 is a constant difference, common difference d. This is a subtraction. Subtraction is a constant. It's called arithmetic. And geometric means this time we do not discuss a subtraction. We discuss the quotient. If this quotient is a fixed number, if an over an minus 1, the current term over the preceding term is a fixed number, this is called a geometric sequence. Okay? So here we list them as a comparison. One is about the difference, the other one is about the ratio. So a geometric sequence may be defined recursively as a1 is equal to a. This is always the first term, the starting initial term. And an over an minus 1 is equal to r. Okay, this is one recursive definition. Or equivalently, where is it? Equivalently, a1 is a, an is r times an minus 1. Just move this to the other side. Equivalently, you see, we have that equivalent recursive formula. Just move this an minus 1 to the right side. It becomes addition. Here is an is equal to an minus 1 times r. So it's r times an minus 1. Okay? So where this an equal to a is and this r common ratio. Ratio is not equal to 0. Those two numbers are real numbers. And a is a1 is the first term. R is the common ratio. A1 equal to A is the first term, right? So that's a parallel sequence. One is about the difference, the other one is about the ratio. Okay, so let's try. For example, if you have A1 is A. What is A2? A2 is R times A1, so it's A times R. What is A3? A3 is R times A2. It's R times A times R is A times R squared. A4 is R times A3. So it's R times A times R squared is A times R cubed. Okay? So that's the first few terms. You just multiply the preceding term by the common ratio R every time to get the next term. All right, so that's a geometric sequence. Geometric sequence. So first, let's check this example. If we have 2, 6, 18, 40, 54, 162, and so on, and this sequence is geometric. Since what? You just check the ratio, 6 over 2 18 over 6, 54 over 18, 162 over 54. I mean, based on the current information, all the ratios are equal to 3. So that's the reason we consider it as a geometric sequence, geometric sequence. Okay? Yeah. So this is a concrete example. And next, let's make some proof. So show that this sequence is geometric. To show it is geometric. To show it's a geometric sequence, find the first term and the common ratio. If you can prove the sequence is geometric, then of course the ratio will be the common ratio. You let n be 1, you will get the first term. Okay? So the main thing is that you have to verify Sn over Sn minus 1 is a fixed number R. Okay? So let's try. Sn is 2 to negative n. Sn minus 1 is 2 to negative parenthesis n minus 1. Be careful about this parenthesis. Okay? So you have to put a parenthesis because there's a negative sign in front of this index n. So this is a 2 to negative n plus 1. So negative n and plus 1. And then let's check the ratio. The ratio is Sn over Sn minus 1 is 2 to negative n, 2 to negative n plus 1. 2 to negative n, 2 to negative n cancelled, so the numerator is 1. The denominator, you still have a copy of 2 here. So the ratio is 1/2, the common ratio. Common ratio. And the first term. The first term is just S1. S1 is a 2 to negative 1 is 1/2. The common ratio is also 1/2. This 1/2 comes from the evaluation for n equal to 1. This 1/2 comes from this ratio as 1/2. They're different. Okay? Okay, so let's do another computation. Show that a sequence 3 times 4 to n is geometric. Yes, it's geometric. Find the first term and the common ratio. Okay, so again, the same thing. You have to figure out what is Sn, what is Sn minus 1. So this place you have Tn. Tn is a 3 times 4 to n. Tn minus 1 is a 3 times 4 to n minus 1. In this place, there's no sign, so you don't have to put a parenthesis. Okay, then the ratio Tn over Tn minus 1 is 3 times 4 to n, 3 times 4 to n minus 1, so it's equal to 4. This 4 is the common ratio, and this fixed number 4, just tells us this sequence is a geometric sequence. The first term is let n be 4. Let n be number 1, so it's a 3 times 4 is 12. The common ratio common ratio is 4. Okay, so here if you want to, you can emphasize So it is geometric. Yeah, let's emphasize it because it's a question. We have to claim it is geometric. When the ratio is a fixed number, then it is geometric. After you prove it is a geometric sequence, you can find the first term and the common ratio. Okay, so here I think I should also mention, so it is geometric as an answer, as a geometric. Okay, so geometric sequence, you just examine this ratio, Tn over Tn minus 1. Right? Next. So let's check the list. Let's go back to the list after the definition. We verify that A1 is A, A2 is A times R, A3 is A times R squared, A4 is A times R cubed. We just copy it. Let's see, we actually already did those computation. You see, here you have 1, there's no R. You have 2, there's 1 R. 3, you have 2 R. 4, you have 3 R. So there's a reason to expect if you have A sub n, it is A times R2 n minus 1. So you see, there's a unit shift. Here's n, here's the preceding integer n minus 1, always. And if you don't trust, you can try the other one. So R times A4 is R times A R cubed is AR to 4. So here's 5, here's 4, 5 minus 1. So this is the formula for the nth term. Nth term of a geometric sequence. Okay, so what is A? A is the first term. So the nth term of a geometric sequence is A sub n. Is always the first term. The first term, let's not write A, let's write A1. First term times R to power n minus 1. Okay? It's a product. And this result is very, very similar to the arithmetic sequence. Do you remember what is the nth term for the arithmetic sequence? Arithmetic sequence A sub n is first term plus n minus 1 times d. So here you see, you always have first term. Because the geometric sequence depends on the quotient, so here is a product with n minus 1 copies of R. Arithmetic sequence depends on the difference, so here is a sum with also n minus 1 copies of d. So it's always n minus 1, n minus 1. This is a sum because originally it's defined by the difference, all the sum. See here, this one is a sum. It depends on how you place this A sub n minus 1. So here it's an addition, so this place is addition. Here is a product, so for the geometric sequence, it's a product. Okay? So just start from the original thing. But be careful, A sub n is always related to n minus 1 in both formulas. In both formula, it is always n minus 1. All right? So that's an important thing. You have to be careful. Okay, so find a pattern. Find a pattern. Okay. Hey, find the nth term of the geometric sequence 10 9, 81 over 10, and 729 over 100. Okay. From the problem, it says it's a geometric sequence. So we believe it's geometric. And this is the first term. This is A1. We need R. What is R? R is A2 over A1, A3 over A2, whatever ratio of the current term and the preceding term, A4 over A3. So you can use whatever number. So for example, you use A2 over A1. It's 9 over 10. Okay? So if you use A3 over A2, it's 81 over 10 and over 9. 81 cancel with 9. It's the same 9 over 10. The same thing. So the R is 9 over 10. First term is 10. Then A sub n is A1 times R to the power n minus 1. A1 is 10. R is 9 over 10 to the power of n minus 1. See, that's it. That is the nth term, of this geometric sequence. And once you have nth term, let's say find the 9th term. Of this sequence. Well, that's easy. 9th term, A sub 9. A sub 9 is 10 times 9 over 10. It's 9th term, so n is 9. 9 minus 1 is 8. In the exam, just leave it like this. We don't really evaluate. We just leave it like this, okay? Find a recursive formula for this sequence. Recursive formula, you name the first term. First term is 10. And then you get an is equal to r an minus 1. R is this, 9 over 10 an minus 1. So this is one recursive formula. This is the answer. You can do this by product, or I say or you can define it this way. You can define this relation by the quotient. This is also correct. You can use either of them as a recursive formula. You don't have to just use one. You can just either of them. One is enough. Okay? One is enough. Okay, so this is the nth term of a geometric sequence. A1 times R2 n minus 1. And then let's try to add the first n terms. We're going to add the first n terms. Okay, so let's try it. Sn. Assume we have a geometric sequence. A sub n is geometric. So Sn is A1 plus A2 plus A3 plus A4 plus An. Right? It's just formal sum. What is A1? A1 is A1. A1, there's no way to simplify. A2 is AR, A times R. A3, A times R squared. A sub n, A times R2 n minus 1. Right? This is the nth term evaluation at each position. A1, it's always A1. First term, always A1. Well, how do we add them? let's try to multiply this sum by r. We multiply the sum by r. Then the first one becomes a1r, and second one becomes a1r squared. Third one becomes a1r cubed. This one becomes a1rn, because you multiply every term by r, so you increase the power. Right? You increase the power. Now I'm going to use row 1 to subtract the row 2. So I have Sn minus Rsn. It's left-hand side. First row minus second row. First row minus second row. Then you see here, A1 survives. Then A1R minus A1R, these two terms cancelled. A1R squared, these two terms cancelled. You can expect this A1R cubed is cancelled with the next term. So you see that this is diagonally cancelled. This one, you have a one position shift. So this one is cancelled with the preceding term. So there's only the last term survives. Okay, do you see the pattern? So you do the cancellation in the diagonal way. Okay, so here you have Sn minus r times Sn. So you factor out Sn, you get 1 minus r. And you divide this equation by 1 minus r. And if you want, you can factor out a1 from the numerator. So Sn is a1, 1 minus r to n over 1 minus r. This is the formula for the sum of the first n terms for a geometric sequence. Remember, what is the sum of the arithmetic sequence for the sum of the first n terms for the arithmetic sequence? Let's state this here. Later we review that one. An is geometric with common ratio r, then the sum of first n terms is Sn is a1, a2, a sub n. It is equal to this one. A1 times 1 minus r to n over 1 minus r. This is Sn. Okay, by this process, and I want to review what is the arithmetic sequence, the sum of first n term. Arithmetic sequence, what we have, an with common difference d. Then what we get? We get the Sn equal to a1 plus a2 plus an. It is n over 2, first term plus last term, or n over 2, 2a1 plus n minus 1 times d. Right? Remember that we have two formulas. You can use either of them. It depends on what information you have. All right? So those two formulas are both important for the exams. Okay? So you have to memorize both of them. This is a review. This is the problem, the new formula we learned today. Okay, now let's check. Find the sum S sub n of the first n terms of the sequence one half to nth power. First of all, this problem does not say the sequence is geometric. So you have to verify or you have to confirm this is a geometric sequence. Okay, so let's check how do we know it is a geometric sequence. An is 1/2 to n, an minus 1 is 1/2 to n minus 1, so an over an minus 1 is 1/2 to nth power over 1/2 to power n minus 1. The ratio is 1/2. So this is a common ratio. So an is geometric. So here you observe or you prove it is a geometric sequence. And the first term is you let n be 1, 1/2. The common ratio after computation is 1/2. Okay, so the sum of the first n terms is Sn is equal to, what is a sum? It's a A1, 1 minus R to n over 1 minus R. Remember that. A1 times 1 minus R to n over 1 minus R. All right? So A1 is 1/2. 1 minus R is 1/2, so it's 1/2 to R to nth power. 1 minus 1/2. This R is 1/2, right? So 1 minus 1/2 is 1/2. 1 minus 1/2 is 1/2. There's a factor 1/2. The denominator has 1/2. They're cancelled. So the sum is 1 minus 1/2 to nth power. 1 minus 1/2 to nth power. All right? So this is the sum of the first n terms for this geometric sequence. And you have to first verify it is geometric, and then you can apply the formula. All right? Because the problem does not say it's a geometric sequence. Okay, now let's try another example. So find the sum Sn of the first n terms of the sequence 1/3 to nth power. Okay, let's try to find it. So first, same thing, you have to verify it is a geometric sequence in order to apply this formula. Okay. So an is 1/3 to nth power. An minus 1, an minus 1 is 1/3 to power n minus 1. So an over an minus 1 is 1/3 to n over 1/3 to n minus 1. After cancellation, you get 1/3. So this means it's a geometric sequence. So it is a geometric sequence. It is a geometric sequence. Okay? So that's our one thing. Once you know it's a geometric sequence, in order to find the n sum, so you need the first term. A1 is 1/3. You let n be 1, so A1 is 1/3. R is 1/3 also. It's just special case. Okay? So the Sn is A1, 1 minus R to n over R. 1 minus R. So A1 is 1/3. 1 minus 1/3 to nth power. 1 minus 1/3. While 1/3, 1 minus 1/3 to nth power, the denominator is 2/3. 2/3 is a denominator, and you multiply it by 1/3, so it's 1/2, 1 minus 1/3 to nth power. Okay, so this is the sum of the first n terms. So you cancel 1/3, 1/3, you still have a 2. 2 is in the denominator, so it's 1/2. All right, so that's the answer. That is the answer. So whenever you have the geometric sequence, the sum of the first n terms is always computed by this formula. So remember, we have two special sequences. One is arithmetic, the other one is geometric. So you always compare those two situations. You have a geometric sequence, you do something. You have the arithmetic sequence, you can do the similar thing. They have the similar stuff. All right? Now let's see something which only geometric sequence has. We have the geometric series. Sequence is a bunch of numbers. You just list of them. You don't have addition, subtraction among them. When we want to find the sum, we say we find the sum of the first n terms. That's it. But from the sequence itself, those numbers are independent. There's no sum or difference among them. But let's see what is the so-called the geometric series. An infinite sum of the form. What is the form? A1 plus A1 times R plus A1 times R squared plus A1 times R cubed and plus A1 times R to n minus 1 and go so on. This one, it looks like we add all the terms from a geometric sequence. We do not just add the first n terms, we add all the terms from a geometric sequence. Because there's infinitely many terms, so that's why it is called an infinite sum of the form. Okay, the infinite sum, it's a form, be careful, we don't say it's a number, it's a form. This is called an infinite geometric series. Infinite geometric series. And we denote it by, okay, so now let's see. We are going to add them from first term to infinity. So it's from 1 to infinity. The general term is A1 times R to the power K minus 1. So we put it here. Okay, so this is a geometric series. We add them. We add infinitely many terms. It's a geometric series. I think it's something I forgot to mention. In this formula, you will see that this R is not equal to 1. The common ratio is not equal to 1. If the common ratio is equal to 1, the denominator is 0. It does not make sense. So what happens if the common ratio is 1? If the common ratio is 1, then what? Then an is R times an minus 1 is equal to an minus 1. So if common ratio is 1, so an is equal to an minus 1. And of course, an minus 1 is equal to an minus 2, and eventually it is equal to a1. So when R is equal to 1, we have a constant sequence. Constant sequence means A1, 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 A1. Just repeat A1 forever. Then the sum, what is the sum? It's just A1 plus A1 up to the nth position of A1 is A1. So it's n times A1. Okay? So for this special case, For this special case, it's not interesting at all. You have a constant sequence, then the sum is, of course, the n copies, n times the first term. So that's something I should mention it when we derive this formula. But let's add it here. Let's add it here. Okay. So yeah, I added something I should have mentioned before. Anyway, let's come back. The geometric sequence. Then here it is an infinite sum of the form. We never say it is always a 0. You see, the sum of first n terms is a1, 1 minus r to n over 1 minus r. It is equal to a1 over 1 minus r minus a1 times r to n over 1 minus r. The first term over 1 minus r minus second term over 1 minus r. This is fixed. It does not change. It does not depend on n. And this one will depend on n. If r is greater than 1, or r is greater than negative 1, less than negative 1, my bad. Let's discuss part by part. If r is greater than 1, r is greater than 1, then r to n will approach infinity. Remember, this is the exponential function. R to n will approach infinity as n approach infinity. Then you will subtract infinity, this is infinity, from a fixed number. It's nothing. The Sn does not exist. It's not as a number as n approaches infinity. As a number, this Sn does not exist, right? If r is less than 1, negative 1, r is less than negative 1, r is less than negative 1, then r of n will approach positive infinity and negative infinity as n even, n approach infinity, as n odd, n approach infinity. So either way, it will be either positive infinity or negative infinity. In Sn still does not exist as n approaches infinity. Okay, so you will get either positively very not large or negatively very large. So there's no such number. The number does not exist. Okay, so if r is equal to 1, remember that we have this the constant sequence. We have a constant sequence, is a constant sequence. For the constant sequence, the geometric series, the corresponding geometric series is a1 plus a1 plus a1 plus a1. It has infinitely copy of a1. Infinitely copy of a1. It is either infinity as a1 is not equal to 0, or it is equal to 0 if a1 is 0. So if you have a constant 0 sequence, the series, geometric series, then the sum is 0. If it's not 0, then you add a 1, you have infinity. You add a negative 1, you have negative infinity. So it will either approach positive negative infinity, or it will be automatically 0. But it's not interesting. If r is negative 1, what happens? If r is negative 1, remember, the sequence becomes what? a1 is here. The next term is r times a1 is negative a1. And next term is negative r times negative a1 is positive a1. Negative a1, positive a1. So you see here, it's an alternating sequence. This alternating sequence also does not give us a solution, because you add these two is 0. You add this is a1. You get this 0. a1, 0, a1, 0. When you do this addition, we want to do this infinite sum, you will repeatedly see A10, 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 A10. You don't get any result. So Sn does not exist as n approaches infinity. Okay, so that's the bad thing. Now let's see what we have discussed. Greater than or equal to 1, less than or equal to -1. The behavior of this geometric series is horrible. So if r is between 1 and -1, if r is between 1 and -1, from the exponential functions, we know this will approach 0 as n approaches infinity. It will disappear eventually. Not disappear, will be extremely small. So when this term becomes 0, a1 times 0 is also 0. Over 1 minus r is also 0. So Sn will approach the first term. First term fixed, it does not change. So we only study the second part. Second part becomes 0. It will approach a1 over 1 minus r as n approaches infinity. Okay, so this long process just tell us, 1, this infinite sum makes sense. 1, it does not make sense. For the first 4 cases, the infinite sum does not make sense because it will be either infinity or just a 0, constantly 0. Constantly 0 means you have a 0 sequence. It's not interesting at all. Okay, so this approach behavior, we call it convergence. Okay, so let's say if Sn approaches a number L as n approaches infinity, we say that the infinite geometric series sigma k from 1 to infinity a1 r2k minus 1 converges to L. If this Sn approach to a number, then we say it converges to L. Otherwise, it is divergent. Otherwise means when this n approaches infinity, this Sn does not approach to a number, it is divergent. Otherwise, the series is a divergent series. Divergent is a divergent series. Convergent, divergent. When you have a convergent series, we write this infinite sum is equal to this L. Okay? Okay, so when does the geometric series converge? When you have such condition. So the theorem, if r is less than is between -1 and +1, means upper value of r is less than 1. If upper value of r is less than 1, the geometric series k from 1 to infinity a1 r2k minus 1 converges to a1 over 1 minus r. k1 over 1 minus r. So this convergence divergence property is totally determined by the value of r. The initial term, first term a1 does not matter. Okay? So for example, remember this example, we had it somewhere. Where? Yes, we had it here. This one. This one. We check here. We find the sum of the first n terms of 1/2 to power n, and from here we get the initial term is 1/2. Common ratio is 1/2. Okay, remember this, and this one, it is equal to the initial term over 1 minus common ratio. Initial term is 1/2. Common ratio is 1/2. So it's 1/2 over 1/2. It's equal to 1. Wow, it's very interesting, right? Let me give you a geometric explanation about this. For example, you have a square. Square has side 1, so 4 sides are all 1. And if you divide it into half, and you color, you get a shadow of the left part, then the area of this left rectangle is 1/2. So you get 1/2. And then you divide this right part into 2 parts, equally into 2 parts. This bottom part, the area is 1/4, 1/4. 1/4 is 1/2 square. So this is the first term. 1/4 is the second term, 1/2 square. And then let's continue this, okay? For this top corner, we divide it into 2 parts equally. And this is 1/8. 1/8 is 1/2 cubed. And then you continue this. This is 1/16. 1/16 is 1/2 to 4th power. You can continue this process. You see, every time you take a half, you will get the next term. Every time you take a half, you get the next term. So you will make this process infinitely many times. And if you do not stop, you will cover the area of the whole square. Right? You will cover the area of the whole square. So if you add them together, all the numbers together, even it's very tiny, add them without missing any term, then the sum has to be number 1. 1 is the area of this square. Okay? So that's the geometric explanation of this geometric series. Geometric series is an infinite sum. It has to be infinite, otherwise it's not equal to 1. If you stop at any position, you will lose some blank region. You don't stop, you will cover everything. Okay, that's the first thing. Second example. Determine if the geometric series sigma k from 1 to infinity 2 times 2/3 to power k minus 1 converges or diverges. First, you have to determine if it is convergent or divergent. If it converges, find its sum. If it's convergent, find the sum. So it's already a geometric series. Let's read this geometric series. Has the first term 2. Remember that, check here, k from 1 to infinity, a1, r2, k minus 1. So the coefficient is a1 is 2, that's the first term. The common ratio is the base 2 over 3, 2 over 3. It's a common ratio. And since the common ratio is less than, ops value is less than 1, it's a requirement. The common ratio must have a ops value less than 1. Since the common ratio has ops value less than 1, the geometric series converges. Right? If you have a geometric series with a common ratio ops value less than 1, it is equal to this, and it converges. Of course, it converges because it will approach to a number. The sum is equal to A1 over 1 minus R, always. So what is A1? A1 is 2. 1 minus R, what is R? 2 over 3. Sum is equal to 6. Sum is equal to 6. That's it. That's it. Okay, so this is the convergent geometric series. This one is a separate property from the geometric sequence. The arithmetic sequence does not have any so-called arithmetic series. There's no arithmetic series at all. No such series, no such name. Only geometric sequence has the corresponding geometric series. Okay? So this is a special property for the geometric sequence. It has a geometric series. When the common ratio R has absolute value less than 1, when the common ratio R has ops value less than 1, the corresponding geometric series converges to A1 over 1 minus R. Okay? Otherwise, the series always diverges. Okay, so let's stop this video and we continue in another video about this same section. Okay, so this page and this page, I do it in the reverse order so you can get all the pages. Okay, next. Okay, this is the first page. Okay, so we finished this video. We will continue in another video still about this section 13.3. It's a very important, it's a very, very interesting. Okay.